Okay, 2.3 is a polynomial of functions of higher degree. It says each monomial in sum is called a term. Terms of a polynomial written in descending degree is said to be in standard form. So that's why we like it to be like x squared plus x plus our constant. Okay, we like our exponents to be in descending order. All right, so a coefficient is a constant number value of each term. The highest degree monomial is called the leading term. And the constant is a number without a variable. All right, so first let's talk about what it means by degree. The degree, when there's only like one variable, if we're just talking about everything's in terms of x, the degree is going to be your largest exponent. And so whatever term has that largest exponent is your leading term. The constant in front of it is going to be called our leading coefficient, and the exponent is the degree of the function. All right, so the leading coefficient test using limits. All right, so power functions eventually rise or fall without bound as x moves towards infinity, whether it's to the left or the right. This behavior can be determined by the degree, and so we're going to check to see if that degree is even or odd. And the leading coefficient. And we're going to check to see if that is positive or negative. All right, so let's look at these first two here, okay? So they represent, oh, and I should have put this here on this last part. Let me back up real quick. Let's see if you can see this. All right, so when they talk about the degree, they usually label it an n, and the leading term is labeled the a sub n, okay? So when you see a or a sub n, they're talking about that leading coefficient. If you see n, they're talking about the degree. Okay, so back here, we can look at the first two. So it says down here, let me see where it's at. There it is. Gotta turn my pen on. I'm sorry, I'm pointing. Y'all can't see. So we see that our a sub n is greater than 0. That means our coefficient sign, our leading coefficient, is going to be positive. And we can also see that n is odd. So that means the degree is odd. All right, so if I have an odd degree, well, let me do this. If my degree is odd, so we always check for the degree, and it's odd, and my leading coefficient, now I'm going to abbreviate that, so I don't have to write it all out. We're going to check on it, and if it's positive, all power functions are going to do the same thing. So they're all going to, and you don't really have to memorize this because you already know what happens if it's odd and positive. So if I have an odd degree, that's like 1, 3, 5, 7, so you know a lot about x to the first and x to the third. So think about x to the first. If it's a positive x to the first, it's going to go up like this. Now, this is one of the very few times we don't read the graph from left to right, is when we're talking about the leading coefficient test, or talking about the end behavior, what's happening on the far left or the far right of my graph. When we're doing that, we're going to start from the middle. So as I go to the left, what's happening to my y values? They're going down, right? So we call that falling. So we say it's going to fall to the left. And then look at it from that center point. If we go to the right, what's happening? My y values are getting bigger. It's going up. So we say it rises to the right. And guys, this is true for every one of them. So you see the example they gave us was an x cubed. Doesn't matter what comes after the x cubed. Doesn't matter if it's x cubed plus 2x squared minus 3x plus 7 or something like that, okay? That doesn't matter. The fact is that leading term has an odd exponent and a positive leading coefficient. It's always going to fall to the left and rise to the right. And then here at the very bottom underneath there says the limit f of x as x goes towards negative infinity. So as my x's are getting smaller, what's happening to my y values right here? They're going down to negative infinity as well. All right, so second one here, next to it, we can see it says that a sub n is less than 0, so that means our leading coefficient is going to be negative. And it told us that our n is odd. So I'm going to erase what I have right here. And let's talk about that. All right, so if my degree is odd and my leading coefficient, though, is negative, every time the same thing's going to happen. So the degree is odd, so I'm going to think of x to the first. And if it's a negative x to the first, we know it's going to look like this. So from the center of my graph here, if I'm going to go to the left, what's happening? We're going up. And so we're going to say it rises to the left. And as we go to the right, we can see it's going down. So we're going to say it falls to the right. And that happens with all odd degrees that they have a negative leading coefficient. So it could be negative x to the 101. It's got an odd degree, 101 is odd, and it's got a negative leading coefficient because it was negative x to the 101. Okay? We don't know what's happening in the middle, but we do know, excuse me, at the ends, it's going to rise to the left and fall to, rise to the left, and fall to the right every time. All right. Oops, and then I forgot the little thing at the bottom there. It says the limit as f of x the limit as x goes to infinity of f of x. So we can look at this one here. We can see that as it goes to positive infinity, our y's are going to negative infinity. All right, and so here it tells us our a sub n is positive. So we know we have a positive leading coefficient. And it tells us our n is even. So I'm going to do the same thing. So if my degree is even, and my leading coefficient is positive, what's an even, what's a function that has an even exponent that we're really familiar with? X squared, right? So we know that if it's a positive x squared, it's going to do this. All right, so again, when we do these, we stand in the center of our graph, and what's going to happen is we go to the left. It's going to go up. What happens is we go to the right. It also goes up. So we're going to say it rises to the left and right. All right, and then on the last graph here they gave us, it tells us our a sub n is negative, so we have a negative leading coefficient. And it tells us our n, our degree, is even. So if our degree is even, and our leading coefficient is negative, well, let's see, even degree x squared, so what if it's a negative x squared? We know it's going to look like this. So if I start in the middle here and I go to the left, we're going to go down. Let's go to the right, we're going to go down. So we say it falls to the left and right. Okay, you don't have to memorize these because you already know what it's going to do based on x to the first and x squared. All right, and then we can see here at the bottom of this graph, it says the limit as x goes towards negative infinity of f of x. Well, we said it's going to fall to the left and right, so it's going to fall down to negative infinity. And then as the limit as x goes towards positive infinity, f of x equals, same thing, we said it's going to fall to the left and right, so it's going to fall to negative infinity. Okay, moving on. Well, there we go. All right, so let's talk about the end behavior of polynomial functions, what we were just looking at. So say consider the domain and range for each degree family, so odd and even. As x goes towards infinity and x goes towards negative infinity, what did you notice about f of x or the y values of the graph? Well, I'm having trouble getting my pen to turn on. There we go. All right, so on the even powers, or let's say even, yeah, we can say powers, degree, whatever, okay? On the even powers, the end behavior was the same. They both rise to the left and right, or they fell to the left and right. On odd powers, the end behavior was opposite. So one of them would rise and the other one would fall. How does the value of the leading coefficient a affect the values x goes towards infinity or negative infinity? Well, if that a was negative, then the end behavior changed directions. So if a is negative, so I'm going to put a is less than 0, then the end behavior changed directions. So saying about that x squared was positive x squared was going up, negative x squared went down. It changed directions. And if you look at the odd ones, it did the same thing as well. All right, so end behavior, turning points, and real zeros. Let's do the first part without the calculator, and then we'll look in it to help us finish it up. All right, so we got f of x equals negative x cubed plus 2x squared plus x plus 1. And so what is our degree? First thing is find your leading term. Make sure it's in descending order of the exponents, okay? We want our function to be in standard form. And it is. We have x cubed, x squared, x, and then we have what I call a no x. All right, so this is my leading term. N is 3, which is an odd. My leading coefficient is negative 1, which is negative. So think about that x, negative x to the first, okay? So as x goes towards negative infinity, so as x goes to the left, we can see it's going up. So my y's are going towards positive infinity. As x goes towards positive infinity, so we're going to the right, we can see it's going down, so my f of x is going towards negative infinity. All right, so let's go ahead and put it in our calculator, and we should see something like this. Okay, it may be more narrow, maybe a little wider based upon our windows. And so the turning points, we can see there's 2 turning points here, because the turning points are where it goes from increasing to decreasing or decreasing to increasing. All right, let's do B. So make sure your function's in standard form. It is. Our degree is 4, so it's even. So I'm already thinking x squared. A sub n, the leading term, or leading coefficient, is 1, so it's positive. So I'm thinking positive x squared. So as we go to the left towards negative infinity, our y's are going up to positive infinity. As x goes to the right towards infinity, our y's are still going up towards positive infinity. And so let's graph this. And so your graph should look something like that. The number of turning points we can see is 3. And we can see that both ends are going towards positive infinity. Now, the x to the fourth is what gave us the end behavior, okay? Everything behind it there is what gives us those curves in it. That's what gives us the places that are turning and everything. But when we're talking about end behavior, we're only worried about the left and right, and so therefore we're only worried about that leading term. All right, so the turning points. We hadn't talked about that yet. So it says the graph of f has at most n minus 1 turning points, so the degree minus 1. And so if you look back real quick, here you'll see that when it was x cubed, negative x cubed, we had said there were 2, and then when it was x to the fourth, we had said there were 3, right? So it was our degree minus 1. But now remember, it says at most n minus 1. Means it won't have any more than that, but it can have less, okay? So think about like the parent function x cubed. We know that graph looks like this. It doesn't have any turning points, but it is possible, and we saw that on the a above, that it could have more turning points. It could have looked like this if we have x cubed plus a bunch of other stuff. All right, so the graph of f has at most n minus 1 turning points, points at which the graph changes from increasing to decreasing or vice versa. The function f has at most n real zeros. So the degree is going to tell us how many zeros we have. Okay, this one says at most n because we're talking about real zeros. Remember, some of them can be imaginary. So what's another word for zeros, though? So remember, zeros are also called roots, x-intercepts, and solutions. So they could word it either way. They don't have to just say zeros. Okay, even an odd multiplicity says if a polynomial function has a factor that is repeated, these duplicate roots are labeled as a multiplicity of n. So however many times it's there is what its multiplicity is. And we've seen some of them when we have like x plus 2 times x plus 2 equals 0. If we solve them both, we would get x equals negative 2. Well, so instead of writing negative 2 there twice, we could say x equals negative 2, and it's got multiplicity of 2, meaning it was there twice. It counts as 2 of our zeros, our solutions, our roots, our x-intercepts. So if f has a real zero, c, of odd multiplicity, then the graph of f will cross the x-axis at the point c, 0. So if that multiplicity is odd, it's actually going to cross the graph there, cross the x-axis. If f has a real zero of c of even multiplicity, then the graph of f will touch and turn on the x-axis at that c, 0. So think about this. You have x squared, right? X squared equals 0. So technically this is x times x equals 0, which means it's there twice, right? The exponent tells us the number of times that root's going to be there. And so 2 is even, and so it means it's even multiplicity. And if you look, when you graph x squared, it touches at that x equals 0, and then it turns back around and goes the other way. It doesn't actually cross the x-axis. Now if you think about like x cubed, that means it's x times x equals 0. So it's there, you're going to end up with x equals 0, and it's there 2 times. So we're going to say it's got multiplicity of 3. So and if you think about your graph of x cubed, it comes up, it touches at 0, and it crosses on through it. So it crosses that x-axis. All right, so that'll help you remember whether it crosses or it touches and turns. So the zeros of odd and even multiplicity. So it says use a calculator to sketch. Excuse me, they already did it. F of x equals x plus 2 cubed times x minus 1 squared. In the graph at the right, label the zeros and describe the behavior of the roots. So let's look at our zeros. Our first one is right here. It's at x equals -2. All right. Notice it crosses, so we know it's got an odd multiplicity. But better yet, look at just this part of the graph. Right here, this shape appears to be cubic. So not only is it going to have odd multiplicity, but it's going to be bigger than 1, okay? If my exponent was a 1, it would go straight through it like a linear would. But this has that odd, cubic shape going on. So our odd multiplicity is going to be of 3. All right, and we can see that it does cross, we said. All right, then my next one I have here is right here at 1. And we can see that this is touch and turn. So we know that that means it has even multiplicity. And so if you look at just a piece of it here, just in that little window there, you can tell it does look like it's quadratic, right? So it's probably going to have a multiplicity of 2. Now let's go back to the equation to see how the equation would have told us this. So notice, if I set this equation equal to 0, I would have I would have x plus 2 cubed times x minus 1 squared equals 0. And we say, well, because these are being multiplied, we're going to set them each individually equal to 0 and solve. Now, when you get this, you don't have to write it out 3 times or write it out 2 times. That n right there, that exponent, gives us, whoops, let me come down here, gives us the multiplicity. So our exponent tells us we're going to have multiplicity of 3. And then we take the base part and bring it out and solve it. And so we know that we have a 0 at x equals -2 that has a multiplicity of 3. And look, that was that one right there. It was at -2 like we said, and we're talking about how it appeared to be cubic. So it has multiplicity of 3, but it's odd, so it crosses. Now for the other one here, we don't have to write it twice. We know this means it's there twice, so this is going to be my multiplicity of 2. Take the base part and solve for it. And so we know we have an x-intercept at +1 that is multiplicity of 2. And we can see that right here. We said it was x equals 1, and we said it had even multiplicity. Well, 2 is an even number, and we can see that it did touch and turn. All right, increasing and decreasing functions. We've already talked about these. So it says a function f is increasing. What does it mean to be increasing? You know what it means. It means as we read our graph from left to right, it's going up. This is just the technical definition. So it says a function f is increasing on an interval if for any 2 x values in the interval where the first one is less than the second one, we have the y of the first one is less than the y of the second one. The function is increasing when the tangent line is a positive slope, so it's going up. The function is increasing on the interval. So when we look at this function, we can see that it is increasing right here. And so it starts here when x is 2, and it keeps going to infinity. So we say 2 to infinity. Remember that 2 is not included on, or the endpoints aren't included on increasing, decreasing, or constant, because at that point, that's where it's changing from one thing to the other. It's not actually doing any of those 3. All right, then it says a function f is decreasing. We know what decreasing means. It means that the graph is going down as we read it from left to right. But it says on an interval, if any 2 x values in the interval where the first one is less than the second one, we have the y of the first one is greater than the y of the second one. The function is decreasing when the tangent line has a negative slope, so it's going down. And this occurs on the interval here. Well, we can see that this part here is decreasing. So as x is from -infinity to that point right there, which is -3. And finally, f is constant, which we know constant means is remaining the same. It's going to be a horizontal line. On an interval, if for any 2 x values, we have the y values are equal. The function is constant here on the interval. And we can see it's right here in the middle. So it's going to be from that -3 to that +2. right, so some more review stuff. Maximum, minima. It says for any function f, there exists x1, x2 that contains c, so that all x not equal to c in the interval is this. What is a local maximum at c? Well, the definition says f of c has to be greater than f of x. Then f of c is called, that's just another word for a local. Remember, is relative. Okay, maximum of f. When we're looking for a maximum, remember we're looking for that hilltop. And a hilltop has both sides to it. So I'll talk about that in a minute. So we can see here in this graph, we do have a maximum here, and we have a maximum there. Local, or we could say relative, okay? Now, that may be the maximum of my graph. The absolute maximum, we don't know, because we don't know what's happening outside of this window. All right, but what I was talking about is, let's say, here on the very far left, this part of our graph isn't there. So pretend it's not there. This then would not be a local or relative maximum because it does not a hilltop, okay? It only has one side to the hill. It doesn't have the other side. But in our actual one, it is. All right? Then f is a local minimum at c when f of c is less than f of x. And f of c is called, just another word for local, remember, is relative. So we can see, we know that when we're looking for a local or a relative minimum, we're looking for a valley. Again, it's going to have two sides to it. So we can see we've got a valley right there. That's why this point here would not be a local minimum. Talking about the one here at the bottom, because it doesn't have a valley. It doesn't have the other side to it. Uh-oh. Sorry. All right, so at a local max, the graph changes from increasing to decreasing. On the graph to the right, shade the intervals of increase in green. All right, so even if we don't have the right colors, or we don't have a color at all, let's say, we just have our pencil. So you can always identify these by using different shading methods, okay? So let's say we're going to shade the intervals of increase. Instead of in green, we're going to do a little squiggle. Just tell me what you're going to do. So we can see our intervals of increase. We're going to squiggle right here because it's increasing up to a point, and then it starts decreasing, and then it's going to increase again here. All right, at a local minimum, the graph changes from decreasing to increasing. On the graph at the right, shade the intervals of decrease in yellow. So this time, I'm just going to do loop-de-loops to show my shading. And so I can see my interval of decrease is right here in between the two increases. All right, intermediate value theorem says, in easy language to understand, this theorem states that if you find any two x values where the signs change, then a zero of the function will fall between those two x values on the function. All right, so look here. So they gave us these points A and B, and notice C is in between them, and C is our x-intercept, okay? The zero of the function. All right, so we can see we have this point here, which is x is A, comma, and my y value is below the x-axis, so I'm just going to put it's a negative y. And then we have this other point here, which is B, and we can see it's above the x-axis, so we know it's going to be a positive y. So it says if we have 2 points here, one of them has a negative y, the other one has a positive y, then it has to cross the x-axis in between them. So, example 4 says, use the intermediate value theorem to explain why the function g of x equals x squared plus 3x minus 6 must have a root or x-intercept on the closed interval from 1 to 2. So what we're going to do is we're going to plug in 1 into our function, we're going to plug in 2 into our function, and if one of those answers is negative and the other one is positive, it has to cross the x-axis in between those two. All right, so let's find g of 1. So 1 squared plus 3 times 1 minus 6. So I'm just going to work this out. So I got 1 plus 3 minus 6. 4 minus 6 is negative 2. All right, then let's find g of 2. We'll work that out. So I got 4 plus 6 minus 6. 4 plus 6 is 10, minus 6 is 4. So notice this one is negative, this one is positive. So because one y value is negative, one y value is positive, there has to be a 0 then in between where x is 1 and 2. All right, so we can write that by saying by the intermediate value theorem, you're going to see that every now and then abbreviated like that, there exists a value x equals c, because we don't know what it is, we didn't have to find it, where f of c would equal 0, means its y value is 0, on the interval from 1 to 2, because g of 1 is negative and g of 2 is positive. Now, if they'd have both been positive or they'd both been negative, we wouldn't know. There could be a 0, there may not be a 0. But because one is positive and one is negative, we know the graph has to cross the x-axis between them. Just think about it. If you tried to graph this, you'd have what, 1 and negative 2. You would have 2 and 4. And so if I want to connect those dots, I'm going to have to cross that x-axis. All right, and then concavity. All right, looking ahead to calculus, we need to explore concavity. Our goal is to understand the terminology for now. Later, we'll have calculus rules for finding these intervals algebraically. All right, so it says a function f is concave up on an open interval if for any choice of x1 and x2, with x1 being less than x2, the graph looks like a U or part of a smile. All right, so if it's opening upwards, it's going to be concave up. And so you're looking for that smile, and we can see that. Let me change colors here so it's a little more obvious. And so we can see that right here in this area, right? Looks like a smile. A function is concave down on an open interval if for any choice of x1, x2, with x1 being less than x2, the graph looks like an upside down U or part of a frown. The tangent line will be above the curve if the function is concave down. Shade the graph at right in blue for this behavior. All right, so I didn't even read the shade part, but I just showed you it. And so we can see that there's some point in here where it's got to change from concave up to concave down, right? And so we can see that this here is where it looks like a piece of a frown. It's opening down, therefore it's concave down. Now underneath that, you can't see it on here, but I want to keep the graph, so I'm not going to move it. It says a function f has a point of inflection. Whoops. So a point of inflection, which sometimes we abbreviate is POI, point of inflection. Okay, at C on an open interval I, if the graph changes concavity, tangent line will be above the curve on one side of C and below the curve on the other side of C. Draw an estimate for this in red. Well, I already drew this because I mentioned there's some point here that it's got to change concavity. This point right there is that point of inflection. Its ordered pair will be C, comma, whatever we get when we plug that in. Okay? So we can see here that our graph is concave up. Where is it concave up at? Well, it starts at negative infinity and it's concave up to whatever that C value is. Then it changed the concave down. And so it started being concave down at that C value to positive infinity. And then our point of inflection, we said, was that C, and then what we get when we plug it into the function. All right, one more thing to do here, and then we'll be done with this lesson. So example 5. So I'm just going to write my answers to the side here so we can still see my graph. So A wants intervals of increase. So I'm looking for where my graph is going up. And I can see from D to E and from F to G it's going up. So we said D to E and F to G. All right, B says intervals of decrease. Well, that's where it's going down. So we can see from A to B, E to F, and G to H. So we said A to B, E to F, and G to H. Okay, C says the intervals of constancy. So where's it constant? It's constant from B to D. D said mark and estimate 2 inflection points, K and M. So remember that's where it's changing concavity. So K and M, so just estimates. So our graph is going to be concave down from D to K and from M to H. Kind of running through this quick because the bell just rang. It's going to be concave up from K to M. G, it has a relative maximum value at x equals E and x equals G. Remember, that's the top point. And H says it has a relative minimum value at x equals F. That's that valley. All right, so that's all of 2.3.